Good morning, everybody. Today's lesson is going to be continuing our discussion of the hydrologic cycle. And instead of talking about groundwater today, we're going to be talking about surface water, specifically moving water through rivers, lakes, whatever else. And of course, then the hazards associated with moving too much water through the surface water system will deal with flooding. This is one of my favorite pictures from several years ago. From Grand Rapids, Michigan, and you'll notice this is someone's office window. The duck, of course, is a nice touch for scale, but what you might also notice over here is that the person was in their office as the water was rising and obviously couldn't get out while it was flooding. But here's 3:08 p.m., 10:30 p.m., 4:11 a.m., 5:45 a.m., daylight hits, and then actually it looks like the water crested at around 5:20 or something like that the following day. And at one point, the water was all the way up to here on this person's office window. So flooding, definitely an issue. As we all saw about, say, Hurricane Katrina or other things like that. We experience flooding in Boone on a regular basis, it feels like, most summers and falls. So let's talk about a little bit more in terms of what causes flooding and the specifics of moving water through rivers. We remember from the groundwater discussion, and if you didn't do that one yet, you might want to scoot back and do that one, but the hydrologic cycle tells us that when water rains down from clouds, it kind of has two paths which it can go. It can either end up in the subsurface, right? So it says some water infiltrates and becomes groundwater, and that's what we talked about earlier in the week. But that other water actually will then stay in the surface realm, and it can actually then go into things like streams. It can actually, if the climate is cold enough, it can end up locked up on land in snow and ice. But specifically what we want to do is we want to talk about these little surface collections of water, right? So swamps, lakes, whatever else, little tributaries that then eventually drain all out into what's called a trunk stream. And the trunk stream is the main branch, right? The main part of the river that then the smaller streams, the tributaries, add into. And then, these trunk streams are things that we would talk about, like, for example, Boone Creek, or some of the bigger ones that you're familiar with is the New River, the Watauga, the Doe River, everything like that. So if we're going to talk about moving water in river systems, we'll kind of talk about it in a three-part situation. We're first going to talk about how we collect water, right? So we're going to collect water up in the mountains where we get a lot of rainfall, and that's called the headwaters. So the headwaters of any river, right, are where the river kind of begins, where the drainage systems of the mountains are going to be collecting a bunch of water and funneling it through all of those tributaries into then the larger trunk streams. So the headwaters is kind of upslope, right? The beginning parts of the rivers. We'll then talk about how the rivers kind of change their shape based on where they're located during the transportation phase. We're moving a lot of water and we're moving a lot of sediment, but the amount of water, the sediment, and the steepness of the slope will actually give you a different shape of a river. And then the third part then is that once all that water like moves through the system here, where does most of the water in the surface system want to go? Well, it eventually, right, it all wants to go to sea level, because sea level is a point of equilibrium, right? So essentially we call sea level base level. And water in the system wants to get to base level. So that's why the water from the mountains flows down those slopes, gets into the rivers kind of in the Piedmont, but then most of the rivers are going to end up on the coastal plain. It's because the water in those rivers wants to make it to base level, and ultimate base level is mean sea level. So let's start off by thinking about what's going to happen at the headwaters, right? What's going to happen closest to the area where we're going to be draining the mountains or draining the highlands and collecting all of those water, all the water. So you might have actually seen this. If you drive from Boone to Wilkesboro and you go up 421, or even if you go from, say, Boone down towards Hickory or Lenoir on 321, you may have seen a sign that says Eastern Continental Divide, and then it gives an elevation. What that means is that anywhere where you have a drainage divide, right? So those signs are telling you that that's the continental divide there. It means essentially a line in the mountains where water that falls, so rain that falls on one side of the drainage divide goes to these rivers, and then rain that falls on this side of the drainage divide will go to a different set of rivers. So the drainage divide essentially is kind of usually a high point, right? A ridge or a set of mountains or something like that, where water will kind of collect into different what we call drainage basins or catchment basins. That would be these over here on the side, right? Here's one basin and here's a different basin over here. So we are separating different drainage basins by what's called the drainage divide. So technically speaking, we have a big drainage divide right here along the eastern coast of North America, and that's the sign that you see, right? The Eastern Continental Divide. What that means then is that rainfall that falls on the western side of the Appalachian Mountains flows to the Mississippi River, right? And rainfall that falls on the eastern side of the Appalachian Mountains gets into all of our rivers here and goes to the Atlantic Ocean. We have another very large drainage divide in North America, and that's what's shown here. And if you're good with your geography, you'll know that that's the Rocky Mountains, right? So if this is the Rocky Mountains coming through here, that's another example of a very large drainage divide. Rainfall that falls to the west of the Rockies eventually makes it into the Pacific. But rainfall that falls on the east of the Rocky Mountains gets into all these different rivers here before it finally makes it into the Mississippi River and then gets into the Gulf of Mexico. Now, I'm showing you drainage divides on these maps that are huge, right? Like continental drainage divides. But literally every little valley can have its own drainage divide where it just separates water from this valley goes into, this tributary, this little Boone Creek, this little Winkler Creek or whatever before they finally then feed into the larger rivers. So we'll talk a little bit about river terminology, just so that when I use these names, these terms, we won't get confused. So the first thing, we already talked about the headwaters, right? This is where you actually have your collection, right? This is where you get drainage and collection of water. And then we also just discussed the drainage divide. So you can imagine that in this hypothetical situation, we've got some sort of drainage divide right here so that all the water on this side is now flowing into this hypothetical river system. Okay. So the actual river itself, right, the actual thing that's collecting all the water, we're going to call that the channel. And when we talk about the path that a river takes, we call it the course, okay? The course of a river. Where the river ends up dumping out its water into a larger body of water, we call that the mouth. So for example, the mouth of the Mississippi River is in Louisiana, where we see the Mississippi River Delta. That's the mouth of the river. That's where it dumps all of its water and sediment that it's been carrying across the entire country, and then it kind of drops it all off there at the mouth of the river at the Gulf of Mexico. Okay, so there's another term that I want to get into here called the floodplain. Believe it or not, Appalachian State University is built on a floodplain. Okay, we are built on the floodplain of Boone Creek. The channel is the main conduit for water. The floodplain is all the green that we're showing right out in here. This is all the floodplain. The floodplain is very aptly named, right? Because it literally is the flat plain next to the river that frequently floods. Floodplains are extremely important because to keep a river healthy, a floodplain needs to be able to kind of absorb, slowly, but absorb floodwaters. So you can imagine that when a river floods, so we can imagine that here, if this river in our system, right, if we kind of say that the river actually floods, so this actually becomes a really high river, right? If it floods and puts water all out onto the floodplain, the idea of a floodplain is that slowly the water from the flood will sit on the floodplain, and it will slowly infiltrate into the ground and essentially lessen the impact of the flood, right? So you can imagine the floodplain is kind of like a sponge. It absorbs floodwater slowly, but it absorbs floodwater and helps to then slowly release that water back into the river. Floodplains are very critical for keeping rivers healthy. Now, if you think about Boone Creek goes through downtown Boone. And in many places, it is in a concrete culvert, right? It's in a concrete channel, or it is underground. In fact, it goes under the Raleigh parking lot. Or you can think of it too, it literally has pavement on both sides of it. That's a really big problem, and it adds to the reason why we have so much flood problems, especially near the Rankin Science and Edwin Duncan buildings, because we have paved over the floodplain there, and we've removed that kind of spongy surface and put an impermeable surface there, pavement, blacktop, whatever. And that's a really bad thing. So when you're living around rivers, it's actually really important to keep the floodplains healthy. It helps to minimize flooding, and we'll talk about that more in a few minutes. The other two things that I want to talk about on this slide here are these terms that are slope. Okay, you guys remember from math class or whatever, the slope is just the rise over the run, right? So the change in elevation over distance. You can also call that the stream gradient. So we're essentially saying that, where the stream gradient is really high, for example, up here near the headwaters, where the gradient is high, river channels tend to be very V-shaped, They tend to be very V-shaped. So if you looked at the river in cross-section, it would actually have a very sharp V-shaped pattern. What that means then, and here I'll show you, here's our water right in our channel. What this means is that when the slope is steep, the water will cut down, okay? It will cut down into the local bedrock and make a very steep-sided channel, a V-shaped channel. Where you have then a kind of more shallow gradient, right down here, kind of near the mouth of the river, where the slope is not so steep, you get instead U-shaped channels. So the bottom of the channel is actually very U-shaped. It's gently shaped. The reason for that is because closer to the mouth of the river, where the stream gradient is shallower, the water in the river is very, very close to its base level, right? It's close to sea level. So the water doesn't feel this urge to cut down to get to base level. And instead, you'll notice the river spends a lot more time kind of going back and forth rather than cutting down. So that's what gives these shapes of the channels very different morphologies, right? V-shaped channels, really high slopes where the water is trying to cut down and get close to base level, or you get U-shaped channels closer to the mouth of the river where the water is closer to base level and the river is just kind of happily meandering back and forth. So here's just an example of what this grade or gradient looks like, right? Remember that this is just a fancy word for what's the slope, right? What's the rise over the run? So if we look at kind of where the Rocky Mountains are, and we look at how the rivers drain out there and head out towards, say, the Mississippi River, here is Wyoming and Colorado, South Dakota, Nebraska and Kansas. These are all the rivers and the gradient, the change in level as they move from the Rockies. So the headwaters, right? The headwaters of the Rocky Mountains over here, and then their gradient drops significantly as you move farther and farther away. So remember, look, here's a steep rise over run, whereas over here, here's a shallow rise over run. So if you can remember this, where would you get U-shaped channels? Well, you would get U-shaped channels down here where the slope is relatively shallow, and you would get V-shaped channels up here where you're closest to the headwaters. Good. This idea of base level, right, is the concept that water is essentially trying to get to its lowest elevation. So base level is the lowest elevation that a stream can flow to. For most large rivers, that is going to be sea level. It's kind of a level of equilibrium. So even if, if sea level changes, okay, so for example, say sea level rises by, 100 feet. Rivers that were feeling like they were significantly different in their elevation from sea level may not feel such a difference, because if the river was at 200 feet above sea level and now we've increased sea level by 100 feet, right? We've actually now decreased the gradient significantly, right? So maybe that river won't cut down as much. The opposite can happen though. Say you have a river that is currently 200 feet above sea level, and then we drop sea level another 100 feet. That then means that the river is now 300 feet above sea level, and it will start to downcut and make V-shaped channels, because remember, that water wants to reach the elevation of sea level. So the rivers, the streams, will adjust to any sort of change in base level over time. And those changes in base level over time can be things like, right, sea level changes, or how about this, or tectonics. And what I mean by tectonics is, say that the land surface gets lifted up, right? Say you build mountains and you take a stream that was once at sea level and now you rise it, you increase it up several hundred feet. Right? Now it's going to have to react because base level is below it because it got raised up. So the concept of base level here, just remember, it's the lowest elevation a river can get to, and for most rivers, that is sea level. When you have rivers kind of changing in response to a change in base level, what you then see over time is that the river may be very happy, right, cutting along right here, and its floodplain is on either side doing its little flood absorption thing, and then that's all great and wonderful. But what will happen is that over time, if base level changes, and what we're showing in this graphic is that as you go from panel 1 to panel 2, they're showing that, let's say that the entire area has been uplifted. So you've actually pushed this entire region up. What that means is that the river now becomes a higher elevation, but it wants to reach base level. So what will happen is that the river will start to cut down into its previous channel, and it will abandon its old floodplain. This is the old floodplain that the river was working on over here, right? So now it's making a new floodplain, but notice it's at a dropped down lower level, right? These old floodplains up here, these abandoned floodplains, we call these terraces. And we can actually reconstruct changes in base level of rivers throughout geologic history by studying their terraces. I'm going to post an animation on As You Learn, and I will try to see if I can get it up on YouTube. It might be a copyright issue, but about the hydrologic cycle and about rivers, terraces, downcutting, and all that sort of stuff. So you'll see a beautiful animation that I helped make where they were actually showing how changes in base level can cause this downcutting and leave abandoned terraces. Okay, so we also have to remember that the streams and rivers are not only carrying just water, but they're also carrying sediment, right? They're carrying loose, uncemented material. And so there's the amount of sediment that a river can carry is called its total load, okay? Now the load that a river can carry is actually broken up into 3 different components. The first one is the bed load, okay? The bed load is what we're showing here. This is bed load. Bed load means the sediment that a river is carrying along its bottom, along its bed. So this is the coarse grain stuff, the real heavy stuff that you can't like pick up and suspend in the water. Instead, what you're doing is you're kind of, rolling it along the floor here, you're kind of pushing it or rolling it, and it's kind of just slowly being crept along the bed this way. So bed load is the first thing that we have. Second thing here I'm going to show you is suspended load. Suspended load is all this little fine-grained stuff, right, that's being carried by the water, but it's small enough that it can actually be picked up and then held just in the water flow. You guys might notice this whenever you see Boone Creek turn to chocolate milk after a good flood, right? You notice that the rivers around Boone get really, really muddy and they get really cloudy. That is the suspended load that you're seeing. That's all the really fine-grained particles, things like clay and silt. They're being carried along in the river, but it makes the river look very kind of murky and mixed up. So that's the suspended load. And believe it or not, the suspended load is actually the largest amount of sediment that rivers usually carry, right? So that's the greatest percentage of sediment that a river can carry is usually in the suspended load. We also have to remember too that there is a small amount of stuff that the river water is carrying as dissolved ions. Okay, so technically we also are carrying things like salts, sulfates, whatever else. We're carrying those things, but they're dissolved in the water. Okay, so you don't necessarily see them, but they are solutes that are being transported by the water in the river. So those are called the dissolved load. All these three things, right? Bed load, dissolved load, and suspended load add together to make up the total load of a river. So we want to talk now too about kind of how much stuff rivers can carry. And we'll talk about now the idea of moving a bunch of sediment. And there's two terms. They sound similar, but they're a little bit different. So I want to kind of run through these quickly. The terms that I'm going to talk about is competence and capacity. Now let's just think about this. The competence is the largest particle, right? The maximum particle size that a stream can carry. A good way to remember this, right, is if you're competent at something, you are really good at it, right? You are, you have the highest grade, you have the, the best performance or something like that. So the competence of a river is very similar. It is the maximum particle size, the biggest particle size that a stream can carry. And I'm going to actually amend this. How about at that time? Because if you look at the picture on the left here, notice there's some really big cobbles in this river, right? But at this time, is this river under these conditions carrying these particles? No, it's not right now. But at one point, at some time in this river's history, it was able to move some of these really big cobbles. So at one time, the river had a competence where it could move really big particles. However, that time is not right now because you'll notice you're under very low flow conditions. So competence is the biggest particle, right, that a river can carry. Now the capacity is a little different. Think about what is the capacity of a classroom, right? Usually the capacity of something says, 40 people or 40 seats, something like that. So the capacity is the total quantity of sediment. So you can say, right, like the total load. What's the total amount of sediment that a river can carry? That is the capacity. And again, the capacity will change under different flow conditions. If a river is flowing at very calm, quiet conditions, right, it will have a low capacity. But when it's flooding, it will have a much larger capacity. After we've moved all sorts of sediment and load in our rivers, oftentimes what happens is that material, that sediment, gets dropped off, okay? And so we call that dropping off deposition. So you are depositing, right, the material that is in the river. Now, how do we get sediment being deposited from a river? Usually what happens is as the flow velocity of the river slows down, okay, the particles will drop out. So they will be deposited when the river's velocity slows down. So usually we can kind of correlate this and make a general statement that when the flow of a river is high, right, you're carrying sediment. And when the flow of the river, the velocity drops, that's when you deposit, okay? We actually can calculate the rate at which particles fall, and it is set up this way. This is V here is not the velocity of the river. The V here is the velocity of the settling particle, right? So how fast the particle will settle through a water column. So this is the settling velocity, okay? And it's equal to about 9,000 diameter squared. And they're talking about here the diameter of the particle, right, in centimeters. So if you have an equation where x equals a constant times another constant squared, right, velocity equals just a constant y squared, essentially what we're saying is that if you increase y, you will increase v. If you increase y, you're going to increase v because this is a constant. So Stokes' settling law, right, this equation here of v equals 9,000 d squared, says essentially that the larger the diameter of the particle, the faster it will settle. And that should make sense, right? Larger particles then deposit first, they settle faster out of a flow. And so if you had a jar, and in that jar you had marbles, you had, I don't know, fish tank gravel that was smaller, and then you had sand, and you filled it up with water, and you shook it all up, and you let it sit and let it settle, what you would find is that the marbles would settle first, right? The fish tank gravel would settle second, and then the sand would be on top. Okay? You would see a situation that looks like that. And in nature, we see that too. We call those graded beds. So this is what graded beds, that's one graded bed right there. You go from big particle sizes up to tiny ones because the sediment is settling out of the river based on Stokes settling law. If you zoom in and you look at the picture at the bottom here, you can actually see these are all little graded beds as well, right? Coarse at the bottom, that looks like there's sand or something down here, and then they get really fine up top. So each of these, right, is like a little fining up, a little graded bed right here, and that just tells you that the river was moving fast and then it slowed down, and the river was moving fast and then it slowed down, right? Because the bigger the particle size, this is where the river was moving fast, and then this is where it slowed down. Everything settled out according to size. Good. Wow, this is really strange. I don't know why I actually have this slide again, although we can remind ourselves about the V-shaped channels and the U-shaped channels. And don't forget, by the way, to make sure you watch the animation, right? Don't forget, watch the animation on As You Learn that explains a little bit too about how the rivers change their shape from V-shaped to U-shaped channels. Okay, I know why I had that slide there. That was to remind me that up in the headwaters, where you have essentially the steeper slopes, you get one particular type of river. So we're going to talk about two main types of rivers. The first one is braided rivers. Okay, so we're going to talk about braided rivers. They are found near the headwaters. Notice in this picture down here, I'm trying to remind you, look, here's all the mountains. So we are close to the headwaters. Notice even in this one, right, the mountains are all in the background right here. So we are close to the headwaters and we are on a steep slope. That means we should have kind of, V-shaped or down-cutting channels. But in this case, where we have braided rivers, the name braided river comes from the morphology, right? Look at how they kind of just braid in and amongst each other. They kind of don't use the same channel over and over again. They just kind of hop and move around. Here's another great example. This is a beautiful example of a braided river, right? They kind of cut around and do all this crazy stuff. So these are numerous, very shallow channels, that are separated by gravel bars. Remember, they're gravel because you're very close to the source, and so you're moving quickly, rapid flow velocity, so you have very big sediment sizes. So reminds ourselves down here that we carry very coarse, very big sized bed load, and they can be relatively wide, but they're not very deep. They're very shallow. So if you see this river here, right, this is pretty wide, but it's very, very shallow. You can actually see here's all the gravel bars in between. So these are wide, shallow rivers nearest to the headwaters. They form on steep slopes and they carry a lot of coarse bed load. As you get further and further down on very shallow slopes, okay, shallow slopes now, so this is a good example, maybe like nearest the Piedmont. Now you're going to get a different type of river. We're going to call these meandering rivers. These meandering rivers have very large sweeping bends that we call meander bends. And so this is a great example here, right, of a meandering river, just kind of lazily going back and forth, making these big, wide, sweeping bends. The flow velocity is slower than it is for braided streams, and that's because you're on a lower gradient, right? You're on a much shallower slope. And you're usually on a much softer substrate. So like in the Piedmont, right, you're sitting on soil, not rock, like you would be for meandering rivers. And if you were going to guess, if these were farther from the mountains and kind of on the shallow slopes, you would guess that these probably would have U-shaped channels, right, rather than V-shaped channels. They also carry a wide variety of grain sizes, but oftentimes, and if you'll actually see if I erase this, look at how kind of murky that water looks, right? They often carry a decent amount of suspended load, and it's usually finer grained than the stuff that we carry in our braided streams. Why do rivers meander? Great question. It actually has to do with the way that the water kind of flows in the channel. You probably have noticed, right? Like you're in the car, you've got 1,000 things going on, you put your coffee mug or your sunglasses or your cell phone on the dashboard, and then you'd make a hard left turn, and what happens to your cell phone, right? If you make a quick left turn, your cell phone goes flying to the right side of the car, right? Well, you actually then are exhibiting the same physical principle that is dictating what's happening when water enters a slight curve in the river. Your cell phone or sunglasses or whatever else, right, are kind of being tossed towards the outside of the curve, right? Same thing happens with water in a river. When water enters a slight bend in the river, the water actually gets kind of diverted to the outside of the curve. It's fastest, right? The movement is fastest on the outside of the curve. And then what will happen is it'll make its turn, and then when it comes to the next curve, it'll actually get tossed to the outside again, here. What happens, therefore, is that on the outsides of these curves, you get net erosion. The reason you get that erosion is because you have very fast flow on the outside of those curves. And so you're now going to try to kind of cut into the bank of the river there. On the inside of that same curve, right, if it's fast out here, the movement of the water on the inside of that curve is slower. And so you actually get deposition on the insides of the curves opposite the place where you're getting erosion. So what happens over time is that we set up this kind of feedback, right, where we constantly create these areas where you're getting erosion, right, erosion here and deposition here. And so over time, the river meander is going to move towards the zone of erosion. Remember, the zone of erosion is where we are kind of cutting into the bank, right? So we call that the cut bank. The cut bank is the outside of the meander bend, right? The outside of the meander where we have erosion. And then on the inside of the meander bend, right here, right, this inside where we're actually having slow movement and deposition, we collect what are called point bars, okay? So notice down here, cut banks are areas of erosion, and they erode because they are the fastest flow. They're on the outer part of the meander. The point bar is an area of deposition. The flow is slow there, and you can remember these are the inside of the meander bends. Over time, as rivers continuously flow, they will keep moving towards their cut banks. And what happens is that the meander actually gets more sinuous, right? More meandering, more snaky, more curved over time. And what can happen is that if that meander bend gets so dramatically bent like this, right? During one flood event, what might happen is that the river will be moving this way, and instead of cutting off to the side here, it will actually break and flood and make essentially a cutoff to where the river kind of goes back to a non-meandering look and leave an old meander bend off on its own. That little meander bend becomes something that we call an oxbow lake, right? The river used to flow out here, but we've now kind of cut it off. And so this oxbow lake now, because it's now cut off from the main river, that oxbow lake doesn't get any more water added to it. So what tends to happen over time is that the oxbow lake will dry up. But you might see these on a lot of our images, and it tells you where the river used to flow and used to bring water to that oxbow lake before it got cut off. Okay, a little bit of math here. It's okay, we can work through it, right? we are going to set up something now called the continuity equation, okay? I don't like that blue. How about this? The continuity equation. That's what we're going to look at right here. The continuity equation says that this variable Q, you're going to want to know what Q is, because every time you now have a water well in your house or whatever, remember we set up Q and said that Q is discharge, right? Discharge, and that is volume of water per time. So cubic meters per second. If you're a homeowner, you're going to get something like gallons per minute reported to you if you have a well. Okay, so that's important. That is the volume of water moving by a location per some unit. Gallons per minute, cubic meters per second, millimeters per hour, something like that. Excuse me, milliliters is what I meant to say, per hour. So this Q is discharge. Discharge is equal to, and especially when we're talking about rivers, the width of the river, the depth of the river, and V here is the velocity, okay, how fast it's moving. You have actually manipulated this equation, and you don't even know it if you've ever taken a hose, right, from your house. You kind of attach it to the spigot, you turn the spigot on, right, and the water is now flowing out of the hose. Well, what happens when your annoying little sister comes running by, right, and you want to squirt her with the hose? But she's running too fast and she's just too far away. How do you make that water reach her? What do? You put your thumb over the end of the hose, right? Now, if you put your thumb over the end of the hose, just partially, not all the way, but just partially, right? You have essentially manipulated this part of the equation, because let's define this really quickly. Discharge is the volume of water, right? So that you set by essentially turning on the faucet, right? So when you turned on the faucet at the house, you set the discharge. Now let's relate the rest of this here. The width times the depth, that is essentially a synonym for the area of the hose, yeah? And the velocity is set, of course, too, by however much, what the flow rate is in your water pump or your water system. So that's already set. You haven't changed anything like that. So when you want to squirt your little brother or little sister, what do? You essentially decrease the area of the hose by putting your thumb over half of it. So if you manipulate this equation by putting your thumb over half of the hose, did you change the faucet at all? You didn't go back to the house, right, and change the faucet. So that didn't get changed. What had to happen? The velocity actually had to increase because you decreased the area of the hose. So you put your thumb over half of it, and now the velocity had to increase because this amount of water still had to make it out of the hose. So the velocity went up, and that means that now the water is squirting farther out of the hose, and you soak your little sister. This is kind of just a really neat way of just manipulating this equation, but hopefully the idea of just using your own household hose, this is the same idea of how we can do this with rivers. If I get rid of all my scribbles here and we think about this too, if you've got a river, right, and it's flowing and it has a certain discharge and it's moving at a certain velocity, say for example you deepen, right, you deepen the river, right, so you say you increase the depth. Will that river move faster or slower? Well, if you increase one variable on this side, but this has to stay the same, that means that this variable has to move in the opposite direction, right? So if you increase the depth, if you deepen the river, it will slow down. The other way works just as well, and we see this happening in a lot of the rivers around Boone, right? If you take a river and it has a certain, width and a certain depth, remember, by the way, this is equal to area, right? Width times depth is equal to the area. If you have a river that has a certain width and depth, and then you change that, right? Say you actually now decrease the area, maybe say you fill in, right, part of the river channel because you want to build a road right here or something like that. Now, if you decrease the area, what will happen to the flow velocity in that river? It will have to go up, and then you'll have big problems with erosion. Okay, so that's what I'm going over here. If the area decreases, if the channel gets smaller for any reason, the velocity must increase. And that's what they're having a problem with over on State Farm. Or they used to rather. They used to have big problems with that because they were filling in parts of the New River channel over there and then having problems with downstream erosion. I know you guys have actually probably heard the term too, right? About levees. I know Kim in our class knows a lot about levees because she's from New Orleans, and so she knows a lot about levees and how they can be useful, and how they also can be very devastating when they don't work. Now, levees can be built by humans, and in fact, around New Orleans, there's plenty of human-made, man-made levees. But rivers actually make their own levees as well. So we can get natural levees. In that animation that I've got for you on As You Learn, check that out. That's got a great discussion of how levees are formed. But remember, if this is a river, right, and we have our floodplain on both sides, every time the river floods and overtops its banks, it's bringing with it sediment, right? So you can kind of see down here, during the flood, now the floodplain is underwater and we're carrying a bunch of sediment right out onto the floodplain. So what tends to happen is we create friction right here on the edges of the riverbanks so that when all the water and sediment kind of floods back into the channel right after the flood is over, now all the water has receded, there's this little lump of sediment kind of built up on the sides of the rivers, and after every flood, that little lump of sediment helps to get bigger and bigger and bigger. So these little lumps of sediment on the sides of rivers are called natural levees, and they kind of help to keep water in the channel, and they help keep floodwaters off the floodplains. So natural levees are great, and we as engineers have kind of adopted this natural phenomenon to say, okay, if there are rivers that tend to flood frequently, we can build man-made levees and try to keep the water in using these man-made levees. It's the same principle. We'll talk about what happens when levees don't work in a few minutes, but I also want to kind of now introduce some of the more natural processes that happen with rivers. And specifically, I want to talk about what happens when rivers end, right? So what happens at the end of streams? There's two scenarios that I'm going to show you here. One is what happens when the stream leaves the mountains, okay? So let's imagine that this is actually, this is in California, by the way, right here. So this is California, and this little tiny line, this is a road for scale. So this feature is actually really big, okay? But notice the mountains are right here, cool. And here's the river coming out of the mountains. And what happens, right? This is fast flow up here. It's really fast. The water is coming down the slope of the mountain. It's really fast. And then the river hits a very shallow gradient, okay, very shallow slope. So what happens to the velocity of the river, do you think, once it goes from steep slope to shallow slope? Does it speed up or slow down? Okay, if you said slow down, you're right. So the water will slow down. And so remember, when the water slows down, the water will drop off all of its sediment. And remember too, you already know that when the water drops off its sediment, it will drop off sediment where it drops off the coarse stuff first, right? The coarse stuff drops out according to Stokes' law first. The finer stuff, right, will drop out second. And it actually drops out in this beautiful kind of fan-shaped feature. And then the really fine-grained stuff will drop out last. So this kind of fan shape or lobe-shaped feature is called an alluvial fan. Alluvial just means from a river. So this is an example of an alluvial fan. And alluvial fans are only found right near mountains. So we have alluvial fans in a lot of places like near the Rockies or whatever else. Beautiful examples of alluvial fans. And that is just the sediment being deposited when the stream slows down once the river exits the mountains. If we were essentially to look at an alluvial fan from the side, right, we literally, if we just kind of cut it and looked at it in a cross section like this, okay, what you would notice is that you've got big stuff up here smaller stuff, even smaller stuff, and then fine-grained kind of clay stuff out here. So alluvial fans do this thing that we say they fine outward. Okay, so essentially they get finer as you get away from the main exit point. Okay, so these are alluvial fans. They're often found in arid regions or semi-arid regions, but they just are forming near the mountains. So this is what happens when a river leaves the mountains and drops off all of the sediment that it was carrying. This is very different from another feature that we call a delta. Deltas happen when rivers kind of enter into a standing body of water, like a lake or an ocean. It's a similar principle, right, in that the river is going to be doing its velocity thing. It's going to be moving quickly and carrying all of its stuff. And when the velocity of the river drops, it's going to then drop all of its sediment. But the reason why the velocity drops here is not because you're leaving the mountains. Instead, it's because you're entering a standing body of water. And so when a stream enters a standing body of water, the velocity drops, you deposit your sediment, and you get a delta. Here's a beautiful example of the Nile River Delta, right over here on the left. And I've just changed the north direction here, but you can see here's the river doing its beautiful thing. This is the Mediterranean Sea right here. And so what happens is when the water meets the Mediterranean Sea, it slows down and you create this beautiful capital Greek letter D-shaped feature called a delta. Here's another example of a delta over here. This is a very pretty, very different looking delta, right? Here's the water coming out. Here's the standing body of water. And it's not quite the same shape, right? This is what's called a bird foot delta, but it is the same principle, right? That the sediment gets dropped off because the river is meeting a standing body of water. These are not found near the mountains. Instead, these are found near the coasts. Okay, these are found near coastlines. Because that's where you're going to get, of course, your large bodies of water, right? Big lakes or the ocean. Deltas can actually move, and I know that Kim is very aware of this, especially being from New Orleans. Deltas can kind of move, and what will happen is that over time, as like the delta keeps depositing sediment over here, right? More and more sediment gets deposited. This will actually get filled up and will become kind of like a high point. And so as this river wants to keep bringing more water and sediment, what will tend to happen is that over time, the river will kind of jump and start depositing sediment over here where there isn't such a high point. When the deltas shift and move like that, it's something that we call river or delta avulsion. The Mississippi River Delta has avulsed many, many times in the last, couple tens of thousands of years. And we can actually see where it used to move, where it used to drop off sediment and where it is now are very different. So if you want to take a break, this would be a perfect time to do it because we're kind of at the 48 to 50 minute time zone. So do that. Go ahead, take a break if you want. That would have been the end of our first class for today. And then when you're ready, come on back and we will do the second half. And we'll just talk a little bit about what happens when rivers exceed their ability to transmit water, and we talk about flooding. Okay, for those of you who are back, let's go ahead and finish talking about flooding. It shouldn't take us too long at all. I'm going to show you some impacts of major flooding. And there's a really great website actually through the U.S. Geologic Survey, and we are going to use it in lab next week. It's called the USGS Water Watch website. And I'm a terrible instructor because you'll notice that I actually haven't updated it. This is a 2018 map of the US. We're going to use literally the map from the day where we're doing our lab. But it's pretty cool because if you want to know what's going on in terms of the state of drought or the state of flooding anywhere in the country, you can go onto this USGS Water Watch website and you can actually see it. So you can see here that in June 11th of 2018, boy, we had a lot of rain and a lot of flooding, right, in the rivers, kind of in the mid-Atlantic states and in Florida. And then also at the same time, we had a pretty bad drought going on, looked like in these regions here, even in the Pacific Northwest, which is kind of odd. So we can actually look at this and we can see that certain rivers are kind of moving at normal levels. That's the kind of greens that you see in here. And then some can be well above normal and some can be well below normal. Here's a good example of what this would actually look like if you were looking at the rivers. Here's August 14th, 1991, the Mississippi River and the Missouri River flowing together here. And then notice that just a couple of years later, we had some massive flooding in the region. And notice now all the blue here is where the rivers, the Missouri, the Mississippi, and the Illinois rivers have actually jumped their banks. They're flooding the entire region around them. And much of the floodplain and, of course, a lot of the homes and farmland around that also were flooded as well. Okay, so what's a flood? Floods are a function of input versus outflow. What are we talking about, input and outflow? It's essentially the input and outflow of water, right? How much water do you put in versus how much water can you move or put out, okay? We see this on the news all the time, right? Here's Kim, here's Louisiana. Here is essentially just kind of a CNN example of, when essentially you've got floodwaters rising and whatever else, showing how deep that is. But a flood is essentially when the amount of water that we put into the river is more than, right, exceeds the capacity, the stream's ability to hold water. When you have too much going in and you can't carry it, you get a flood. So, we've seen a lot of examples of this around Boone or whatever. This image on the right here is just me being a little bit of a smart butt. Notice it says here on the sign, open waterfront dining. However, these are all sandbags. This whole wall right here is sandbags trying to keep the water out of the McDonald's. We actually have to do this with Rankin West. I don't know if you've noticed that there have been pallets of sandbags around Rankin West, probably for the last several years. And every time we have a heavy rain, we have to sandbag the groundwater, the ground floor of Rankin West, because we get too much input, and the drains in that little kind of courtyard between Rankin West and Edwin Duncan, the drains can't handle it because they actually were put in too small. And so we get massive flooding and lots of water flowing through Rankin West. So what are the characteristics of a flood? If you ever hear this on the news or on the TV or whatever else, you may often hear these two terms, the flood stage and the flood crest, okay? The flood stage is the current elevation of the water level, okay? So for example here, when you say that the elevation of the water table is at this stage, that says that it is essentially, 12 feet above whatever, sea level. So here in the example of this is the James River, and I stole this because my mom used to live down by the James River in New Bern. But here's an example where you can denote, and they actually do this on the news quite often, that, a river is considered in flood once it reaches a stage of X. So for the James River, right, once the James River reaches 12 feet above sea level, that is what they consider flood stage. Okay, that's when the river is at an elevation that they consider, okay, we've got problems. Now, the other part about terms here that you might often see is the crest. Okay, what is the crest of a flood? The crest is usually the maximum stage. And so we hear this a lot around Boone, where if we're having really heavy rain, they will talk about the stage of, say, the New River or the Watauga River, and they will say it is expected to crest, at 1 p.m. tomorrow. So essentially, it is expected to reach its maximum flood level, okay, its maximum elevation by that time. So here, this is telling you that the crest of this flood here was at 15.6 feet above sea level. So that was the crest right here of this flood of the James River. So we can monitor the streams, kind of the general behavior of streams. And in fact, we actually have a boatload of monitors installed in the different tributaries around campus. So Boone Creek, the department chair of the Department of Geology and Environmental Science, Bill Anderson, he is a hydrologist. So he is somebody who studies water movements. So he literally has a bunch of sensors in Boone Creek, and he literally has it set up to where it alerts his phone So if there is a rise in the stage of Boone Creek near campus, because his office is on the ground floor of Rankin West, his phone beeps whenever the monitors say that the stage of Boone Creek is rising. And so he knows to alert somebody to go make sure they put in the sandbags to keep the water out of Boone Creek, out of Rankin West from Boone Creek. But he also monitors how rivers behave over time and kind of monitoring how often they flood and what it looks like when they flood. And he does that through something called a stream hydrograph. Hydro, of course, means water. So this is a hydrograph. It's a graph of the stage, the elevation, right? I shouldn't say, it's not really the rate of flow. It's actually the stage, right, of a river at a certain time at a certain location. So here's an example, right? This is the middle fork of the New River at Boone. The y-axis over here is the stage, right? What is the elevation of the river? And then this is time, right? And you'll notice that it's actually doing 1 p.m. and it's doing it by every 24 hours. So it's literally showing you every day at 1 p.m. it's taking a measurement. So you can say here that if it says the flood stage is at 12 feet, did the middle fork of the New River during the time of this hydrograph ever reach flood stage? Well, no, it didn't, but it certainly had a couple peaks, right? It certainly had a couple peaks in the hydrograph, and it crested at about 8.96 feet. So this thing here, right, this graph, this is one of those hydrographs. And we're going to use these in lab next week as well. And I'll show you kind of how we actually can look at how historical floods in a river can help us predict how they will behave in the future and how we can deal with it. One of the things that we can use these hydrographs for is to try to figure out whether we can predict, right, what's the likelihood that a certain river is going to flood at a certain interval, right? What's the recurrence interval that you'll get a massive flood every 10 years or something like that. So we can create something called a flood frequency curve. And what we're doing is we're predicting what's the probability. Now, again, this is not factual, but what's the probability? What's the likelihood of occurrence? What's the likelihood that a flood of a certain discharge, right? So remember, this is Q. What's the likelihood that a flood of a certain discharge will happen during a certain interval? And this is in years, right? So notice there's 1 year, 10 years, up to 100 years. Look at this graph now and notice that the line is kind of oriented like this. Let's do a couple of examples and then try to figure out what is this graph actually telling us. What it says is that every 1 year, okay, every 1 year, that's the recurrence interval. So every year you have essentially the likelihood of very small floods. Now, how likely is it that you're going to get floods that are of moderate, say 300 cubic meters per second? Well, if we go all the way over to the curve, I cannot draw straight lines on this, guys. I'm so sorry. Woo, I'm terrible. If we then have this curve is correct, what this tells us is that the probability of getting a flood of about 300 cubic meters per second is probably on the order of every 75 years. This is essentially telling us that the bigger the flood, right? The bigger the flood, the longer the amount of time in between subsequent floods of the same type. So every year, every year, we will likely get a small flood. However, the really big floods, right, really big floods only happen maybe every 100 years. And you may have heard this term too. I mean, especially around campus, you might have heard, oh my gosh, this is the 100-year flood. Okay, what that means essentially is that we only get really big floods rarely. And those 100-year floods, right, are usually the ones where you actually have, campus buildings shut down and whatever else. But those happen on the order of every, 100 years or so. And it is more likely that every year you will get very small floods. And I tell you, having an office in Rankin Science, I can tell you we definitely have multiple floods, small ones, every year. So we can predict, right, of course, if we haven't had a really big flood in, 85, 90 years, we might be due, and we can kind of start to plan for, okay, the 100-year flood usually kind of happens, and we're looking to plan for it when it does come around. So the magnitude and frequency of flooding actually can be also predicted, and you can do this mathematically by calculating something called the recurrence interval. So remember, what causes a flood? Flooding is a result of the amount, right, the volume of water, and the intensity, right, how much over how much time that you're getting, like rainwater and runoff. And so you can actually check out this discussion on the USGS Water Watch website about 100-year floods. But we can calculate the recurrence interval of certain floods, certain magnitudes of floods, and we're going to do this in lab. But to save some time for lab, when we do this, I'll introduce it now. The recurrence interval is R, right? So the recurrence interval is going to tell us, essentially it's going to be in units of numbers of years. Okay, so how many years between different floods of different types. And we're going to calculate the recurrence interval of certain floods by this equation here. R equals n plus 1 divided by m. Okay, what is n? N is the number of years we have on record. Okay, so the number of years that we have monitored a certain river and we know its flooding history. So the number of years on record. So you might be putting in like, I have 65 years, right, of records of the flood history of this river. So you would plug in, right, 65 plus 1. Cool. And then M, right, you would put M over here. M is the rank of the flood that you're looking at in terms of recorded years. That's great, Dr. L. What are you talking about? In that 65 years worth of data, what you would do is you would go through and you would look at every single flooding event, okay? And you would rank them by their discharge, okay? So if you had, say 2,000 cubic meters, 1,000 cubic meters, and 500 cubic meters, if you had 3 different floods, right, you would rank these so that this would be number 1, that would be number 2, and that would be number 3. So if I want to know the recurrence interval of the 2,000 cubic meter flood, right, I would plug in then the rank of 1 in the denominator here. Okay. If I wanted to figure out what's the recurrence interval of the number 3 ranked flood, I would plug in 3 in the denominator here. So like I said, we're going to practice this in lab, but it's pretty cool because you can actually then calculate what's the recurrence interval. How often, right, after however many years, should I see a flood of this magnitude? So we'll play with that in lab, but for right now, let's talk a little bit too about upstream and downstream floods. Like I said, my mom used to live in New Bern, and I live up here in the headwaters of some of the same rivers. And so an upstream flood would be something that we would see maybe something around Boone, right? An upstream flood happens when you get tons of water, right? Lots of water in a short amount of time. So this is usually a localized area, but it's near the headwaters. So it's in an area that's close to the headwaters and you get a ton of rain. And what happens is that the rivers just can't drain all that rain off the surface fast enough. And so you get kind of a localized flood, and then it dissipates pretty quickly as that water eventually heads into all the trunk streams. A downstream flood, and so let's imagine that this is someplace like, New Bern or Wilmington or something like that. A downstream flood is a little bit more dangerous because it may not have even rained, right, in New Bern, but it rained up in Boone. And all this flood water gets into those big trunk streams and then heads down towards New Bern. Well, the rivers around New Bern can't handle all the floodwaters coming down from Boone, and so they actually then start to rise and flood, and you get what's called a downstream flood. This usually happens after long storms, when the soil is saturated, and oh, by the way, those storms don't even need to be local, right? They can even be storms the headwaters, right? But they can also be from storms nearby. So the soil in the area is already saturated, right? The floodplains really can't sponge up any more water. They're already saturated. And so you get increased runoff that affects a really wide area. What will tend to happen with these upstream and downstream floods is that Boone will get a kind of a summer storm event, right? You'll get a day or two of pretty big rain. Boone will flood for the day. And then usually what happens is the next day, you can actually, on that USGS Water Watch website, you can see the kind of slug of floodwaters moving its way through the state as it's heading down towards the coastal plain. So humans and flooding are definitely kind of a pretty bad combination. Here's a great example, right? This is, I'm trying to see what, that might be a Pennsylvania license plate. I can't tell actually what the blue is. That's an older style license plate, but you can imagine here's just folks having to be rescued essentially because floodwaters got so bad that it actually stranded them in their vehicles. Human activity is unfortunately increasing both the magnitude and the frequency of flooding. So I can guarantee you that this is coming soon to a quiz or an exam near you, right? Human activity is increasing both the magnitude, right? How big is the flood? And the frequency, how often do we get the floods? And you can kind of think about, why is human activity increasing the magnitude and frequency of flooding? What are we doing as a human population that is actually affecting our river systems? The biggest thing is urbanization. And I'll talk about this on the next slide, but I kind of want to say urbanization. And what do I mean by that? Buildings, right? Buildings, roads, right? And I'll put in here like parking lots, pavement, whatever else, you name it. Boy, I can't spell today. All that sort of stuff, right? All of that, roads, and this was supposed to say, there we go. Now you can read it. Pavement. We are channeling rivers, right? We're putting rivers under parking lots. We're putting rivers in concrete tubes. We are changing the way that rivers behave. We are building on floodplains. We're putting shopping malls on floodplains, Boone Mall. And so a lot of these things are a big problem because we're removing the natural process of floodwater getting into the floodplain and then slowly going back into the river. And instead, we are now covering those floodplains with impermeable, right? Impermeable, water can't flow through it, surfaces, which means that the water then just pools up on our roads, our pavements, our shopping malls, whatever, and it actually increases the magnitude of the flood. I happen to like this, I don't remember who sang the song, but they paved paradise and put up a parking lot. You guys know, I don't know, you probably know the song. I'm probably also telling you my age by remembering this song, but here's another great example, right? And I love it. Here's some college students that were pretty happy to deal with some flooded parking lots, right? They were okay with it, but this is UNLV, right? This is actually in Las Vegas, but same idea. They had too much water, but I also think it's very telling that it is a parking lot that has flooded because, remember, this was probably near a river, but also there was too much water, and because the parking lot is covered in pavement, the water can't slowly sink into the ground, and instead it pools up and it makes a big flooding situation like this. Guys, we see this on State Farm parking lot all the time. We see this, believe it or not, in the Duncan Rayleigh parking lots a lot of times too. The parking lots definitely back up because the drainage can't handle all the water that's being piled up on the parking lot surfaces. So essentially the link here between urbanization and flooding is that when one goes up, right, the other goes up. So we see this kind of very natural increase is how much, this is overbank flows. So you can just read this as number of floods, right? And this is the degree of urbanization, right? So as urbanization goes up, right, the number of floods also goes up. This is the Hardys, right? Just off campus there in July of 2013, and you can see this is what it looks like, a little Ford truck trying to make its way through there. There were actually standing waves moving through the water that was there at the Hardys. That was a pretty decent flood we had in Boone. So we see these quite often. But the important take-home message here is that as the percent of urbanization goes up, right, as we have more buildings, more parking lots, more impermeable surfaces, so does the number of annual floods. And so does the magnitude, so does the severity of those floods. Add in hurricanes, and you've got a really big problem. So my apologies to Kim. I'm going to keep this North Carolina centric for the time being. But of course, remember too, Hurricane Katrina was a great example of this because you had flooding in rivers from rainfall. You added then a ton of rainfall from the hurricane system coming through. And of course, then flooding was massive. Let's talk a little bit about North Carolina. If you were here in 1999, oh God, I don't even want to ask. Were you guys born in 1999? Don't answer that. I'm going to feel old. In 1999, okay, we actually had back-to-back hurricanes. So Hurricane Dennis hit first, and just a couple of weeks earlier, and then Hurricane Floyd came in and dropped 17 inches of rain on the coastal plain of North Carolina. And so you can see my little GIF down here. This is from NOAA, right? The National Ocean and Atmospheric Administration. This is showing you essentially the Hurricane Floyd moving its way onshore. Hurricane Dennis had just hit, and so all of the rivers in North Carolina were already significantly swollen and were dealing with tons of, they were at capacity or over capacity from Hurricane Dennis. Then Hurricane Floyd came in as well. All the soils on the floodplains were already saturated. All of the rivers were already at bank full capacity. And so nearly, look at the statistic, nearly every eastern North Carolina river hit the 500-year flood stage during Hurricane Floyd. Remember, 500-year flood stage means it is at such a high magnitude that you should get only one of these floods every 500 years. Well, there it was in 1999, and it was because of these back-to-back hurricanes. Many of people actually called this the Bay of Pigs event in North Carolina because the river contamination was so severe. The flooding, what happened here is that the flooding of the rivers, you know that North Carolina is very popular for pig farms, chicken farms, whatever else. And so the pig and chicken farms that were flooded ended up, tons and tons of pigs and chickens perished in the floods. And that's what you're seeing here. This is a flooded pig farm. And so now you have all the dead and decaying animals from these farms getting into the river water. And as the river slowly started to recede, all that contamination from the pig and the chicken farms got into the rivers and then, of course, washed down towards the coastal plain. Now, remember, I was telling you, my mom lives in New Bern, which was kind of right here. And they actually still, to this, till 2019, actually, they still had warnings that they should not eat the shellfish coming out of the Neuse River. And part of that was because of the contamination that happened in 1999 from all these pig and chicken farms sending all of their contamination into the rivers that then emptied out onto the coastal plain. So this is a North Carolina situation, right? This is where Hurricane Floyd and Hurricane Dennis caused North Carolina rivers to hit the 100-year flood stage. Of course, Hurricane Katrina was a similar situation affecting the lower part of the Mississippi River Delta. So, what is going to influence flood damage? What's going to cause a flood to either do a lot of damage to the region or not? Land use of the floodplain is actually super important. If you leave the floodplain relatively untouched, right, and you're just using it, say, for agriculture, or you're using it for soccer fields or things like that, you haven't really altered the floodplain much, right? You're leaving it as a soil sediment, maybe grass or something like that surface, and it can still behave like a natural floodplain. So if your land use of the floodplain kind of leaves it as the natural sponge that it's supposed to be, you won't get a whole lot of flooding. However, if you then changed and made all of this, pavement or something like that, then of course you would increase the flood damage. It therefore, of course, should also make sense that what influences the flood damage is the magnitude and the frequency of the events, right? The rainfall events. If you get lots of rain and you get it very frequently, the floodplain, of course, is going to be saturated and the sponge will be full, and that will then influence the flood damage that you get nearby. What's the rate of the rise and fall of the stream stage? That's a good example here of the when you had Hurricane Dennis and then right after it you had Hurricane Floyd, right? You didn't have time for the river to kind of drop down to its normal levels before you then increased it again with another hurricane. Season, of course, is important, right? We don't get near as much precipitation in the winter as we do in the spring and summer. So, of course, right, we're going to get more floods in the spring, summer, and fall than we do in the winter. Flooding can actually be a big problem too if you've got a huge sediment load. You can imagine, right, if you've got a really, really big flood event and it's moving very quickly, it can pick up really large sediment. Well, if it does that, it kind of becomes almost like a debris flow, right? And it can actually then move logs or it can move boulders, and that can damage a lot of the structures. For example, right, like this river here, this bridge crossing the river here, right, you can actually start to damage some of the structures. The other thing that's important too is if we get really good at forecasting, if we are effective at our forecasting, we can of course now decrease the damage because we can tell people that they need to evacuate or that they need to kind of, move livestock or whatever else in the event that there is a large flood that is likely. We can also control flooding, and this is this idea about building levees. We're going to take that natural concept of rivers creating their own kind of barriers, right, those levees, and we can do it as well, making man-made levees. So a man-made levee is a physical barrier that we build that holds water back from flooding the floodplain. I don't know who this homeowner is down here, but this is a pretty well-built levee structure. I got to be honest. I mean, this is, look at that, flooding all the way around. I would like to know how they get out, though, to go get a gallon of milk. But either way, this was a very well-built levee. And you can see because there's floodwaters everywhere except in his or her home. So genius idea, but these, right, this is the levee. Right, this is you can build a flood wall, right, around a river, but levees are a little bit different. So the levees are kind of wide embankments. They're built along a river. They are usually made from natural materials, right? So sand and sediment or whatever, those are usually called earthen levees. And then they really just are, kind of these broad, but then also tall earthen embankments that are hopefully going to provide enough protection so that if the river level does rise, this holds the water from getting to the houses, right, that are behind the levee. So levees along the Mississippi River, you'll notice that it says the statistics here, there's more than 2,000 miles of levees. They range in height from anywhere from 15 to 30 feet tall, and they may be 8 foot along the top, right? That's the width of them just at the top, right? They can be significantly wider along the base. They can be up to 100 feet at the base. Levees work really, really well when they work, okay? We have a situation like Hurricane Katrina where levees in some regions held, but if the amount of floodwater is too great, the levees can break, and that can be absolutely catastrophic. Here's some examples, not about Hurricane Katrina, but here are, so here's levees, right? Here's a levee that was built along here to keep river water from hitting these agricultural fields behind it. And now, of course, you can see that the levee has failed. So literally just the sediment has collapsed. And now all the water is from the flood is rushing in and has flooded all the agricultural fields. Here's another one from Illinois, right? Here's the levees that were built, and now this stuff is all flooded. It looks to me, this might be a silo or something like that over here. So there might have been a farmhouse right here that's now been flooded by the water coming in when that levee broke. Levees work for the most part, and so as long as they are kind of reinforced and whatever else, they can be very effective. Another way that we can control flooding is to use something called a retention pond. I was born and raised in New Jersey, and in the Northeast, retention ponds are like every housing development has one. Every shopping mall has one. It's interesting. I don't know why in certain areas, because, well, I guess I do know why. We were at the coastal plain, and so that's probably why we used to see them a lot more often. In New Jersey, at least where I was, is because we were down at sea level. So flooding was a much bigger problem than it is around here. Okay, what's a retention pond? It essentially is a reservoir, right, that stores water until you can safely release it back into the nearby river. In an area where you have a lot of paved areas, so near housing developments, near shopping malls, near strip malls, or big parking lots, these are places that have a lot of impermeable cover. So what tends to happen is that you get a lot of water collected on those paved areas. Instead of sending that water back into the rivers immediately, that's not the river. Instead of sending it back into the river immediately, causing the river to flood dramatically, what a retention pond does is it essentially sends all the water from paved surfaces into kind of like a holding pen, right? And so you keep the water in the holding pen until the stream has come back to, normal or close to normal conditions. And then you can slowly release that water back into the stream. If you look at the graph at the bottom here, what we're trying to show is here's discharge, right? So here's Q and here's time. If you don't have a retention pond, you get this massive amount of discharge over a short period of time. And what that means is that you can essentially flood the land surface. However, with a retention pond, what you'll notice is that you don't ever reach that really, really high discharge, and it's kind of spread out over a long amount of time, right? So you may not get a flood. You're holding that water here until it's time to slowly reduce it back into the stream, and therefore you decrease the magnitude of the flood. So lots of retention ponds can actually be very helpful to kind of mitigate and control flooding in an area that has a lot of impermeable surfaces. Again, think of those shopping malls or whatever else. We can also physically alter the shapes of channels so that we can kind of maintain flooding hazards and kind of, control the ability of a river to flood. We can remember, if you've got a relatively shallow channel, right? If you have a channel that is flooding much too often, you can then go ahead and deepen that channel, giving it more surface area for the water to flow through and decreasing the velocity as well. All the space down here now means that the water can actually then rise whenever it floods, but it won't overtop the banks of your river. So we can actually then use this idea of channelization, right? You can physically alter, you can deepen the channels. And here's an example where we've actually had a channel that used to have a big meander bend in it like this, but instead we've cut it off to essentially now make it a straight channel. My guess is here, what they're trying to do, I think these are fields out here, and this meander bend probably used to flood, it would overtop its banks out here, and so it would probably flood the fields. And so what they've done essentially is to create a straight channel so that now this meander bend doesn't affect the fields that are nearby. So you can actually create this new channel that cuts a straight line and keeps the flooding from your agricultural fields or, your housing development or whatever you're trying to protect. We also have a kind of a more natural idea here of stream alteration or stream restoration. We've done this to Boone Creek, actually, and in many situations, it's kind of a healthy alternative to managing streams, because you're just essentially helping the stream do its natural thing by adding a little bit of resistance so that it doesn't erode in certain areas and deposit in other areas. You can modify the stream to kind of induce, you can say erode here and deposit there by kind of manipulating the cut bank and the point bar. So here's an example. What we do in a river is, so if you've got, water flowing through your river like this, right? And it wants to come out here to the cut bank and it wants to erode here at the cut bank, what you can do is you can use this stuff called riprap. That's what this is, okay? these blocks of, they're natural rock, sometimes they're concrete or whatever. You can actually now use riprap. This is very resistant to erosion. So this is really hard. It doesn't want to break down stuff. You can kind of install riprap in this area here. And what that does is it stabilizes the cut bank so that you don't have as much erosion. Same idea. Notice that they've got a big meander bend right here, and they've installed riprap all along that cut bank, hoping then to not get as much erosion there so that they don't kind of augment the sinuosity of the creek in this region. If you look around Boone, there are several different streams where they're restoring right now. They're doing it on State Farm and all along the greenway of the new river. They are taking local rock, and a lot of it actually is the shady dolomite. It's the shady formation from over in Tennessee, and they are taking blocks of it and just kind of pounding it into, they're pushing it into the cut banks of the rivers, and it's helping to stabilize and decrease the amount of erosion to keep the stream kind of in its channel and doing its normal meander. The last thing I want to introduce to is what can we do to control flooding? Well, we can have just government regulations that say maybe you shouldn't build on a floodplain that floods every couple of years or every 20 years. This is actually very important, and it is causing also a lot of strife when we change the regulations when there are already things built in the floodplain. So in the 20-year flood zone, okay, in the 20-year flood zone, the legislation says actually that you should have no construction at all. This is a new regulation because, as you can tell, Varsity Gym is built right up to the floodplain of Boone Creek. So obviously this is new legislation that wasn't in place when Varsity Gym was built. But what they're trying to do right now is to say that in a zone around a river, right? So in a zone around a river that we know is essentially prone to flooding at least once every 20 years, we're trying to build nothing at all. So there's no risk of anything getting damaged within the 20-year floodplain. Now, the other idea is that in the 100-year flood zone, right, so in the area around the river that should get flooded only maybe once every 100 years, the only construction that can be put in there is construction that has been flood proofed. So things that are built on stilts, right, or things that have maybe open basements or something like that that can deal with being inundated, even if it's only once every 100 years. So this is a preventative measure that's very, it is controversial because you can imagine, right, this happened to one of our faculty members in the department just a few years ago. She had a farm in Ashe County, and she was built on the 20-year floodplain. The house had been built for 100 years. And what happened is that her property was assessed because she was trying to get a home loan, and they noticed that she's in the 20-year floodplain. And so they told her, this house isn't supposed to be here. Because you're in the 20-year flood zone, we're going to have a reassessment of the insurance on your house. And when they did that, her homeowner's insurance went up, and I think it was something outrageous like $6,000. In 1 year. And she was like, I didn't do anything differently. It was just a reassessment of these new regulations that caused her homeowner's insurance to go up like $6,000 a year because they reassessed the flood zone. All did turn out well with that. She was able to work with the local, the county government on that, and it didn't end up costing her a ton of money in insurance. But that is a big issue, right? That with these regulations here is, what do you do with stuff that has already been built in those flood zones? Flood insurance is a really big issue right now. And I was kind of wanting to hear your thoughts on this. This was from 2014. It was actually on the cover of Time magazine. And there are really two sides to this. And I usually do a discussion with my classes on this one about the idea of flood insurance. Essentially says that this 2014 article suggested that restructuring of the flood insurance program, that the insurance rate, so the amount of money that you pay, should reflect the risk. Okay, so if you live close to the Mississippi River, right? And you, according to the new policy, said if you choose to live there, you should have a higher insurance rate. When they applied this new restructuring, one homeowner in New Orleans saw an increase in their flood insurance from $633 a year to $18,000. And let me reiterate, that is per year. Well, there was a huge, as you can imagine, a huge uproar from the public, right? Their rates were certainly going to increase. And of course, where was that money going to go? It was going to go to the government. And the government has now kind of backed down from that idea of the reform. I think this is kind of, this is a good time to actually make people think about this a little bit. The reaction was kind of twofold. Those folks that were living in very flood-prone areas, many of them had lived there for generations. This was their home. This was their family's home. It was all they had ever known. And so it literally, the increase in the rate would have killed communities, right? Plenty of people who had, spent their entire lives, their great-grandparents had had houses there. Many of these, it is unfortunately, many low-income communities are often marginalized and put in these flood-prone areas. So many of those people couldn't move or couldn't pay the increase in the flood. And so lots of people were saying it's plain ridiculous, right? That these increases to anybody seemed like they would be okay, that would be doable. There was the other side of this, actually, and so I want to kind of say that there was a lot of other people who were then saying, well, wait a minute, why should we have a plan in place, which there are plans in place right now that said that if you live in a flood-prone area, we actually will help lower your insurance, we will help subsidize you. And so some people were saying, well, that's silly. Why would you want to encourage people to live in those high-risk areas? So there's, I think, a lot going on here in terms of flood risk, flood insurance, and why individuals may be living in those areas. It may not be a choice, and it certainly may not be something where you can just say, well, if you can't pay the insurance, then you should get up and leave. So think about that. Think about the implications of that. And if you'd be interested in talking about this with me, I'd be more than happy to have a little discussion about this. And we'll probably do that when we do our lab next week on the walking field trip, right? We're going to be talking about surface water and flooding. So keep that in mind. I kind of want to hear from you guys about some of the sides of this flood insurance question. Okay, that's all for today. And so I will, don't forget you've got your quiz on Monday as usual. And if you're listening to this on Thursday of week 3, just remember that we don't have a lab this Thursday. So I will see you guys next week. Okay.